Hi there, Turgeon here, bringing you physics from afar. Session 2 of the MCAS. Let's go. A continuation where you are writing extra onto your answer sheet looks something like this. Actually, technically going back to session 1, this is question number 21, really all about the definitions of heat, temperature, thermal energy. So let's remember this. You might want to write this down, rewind the video if necessary, but heat is a flow of energy. Heat is caused by two objects being at different temperatures. Temperature is about molecules. Temperature is a measure of how much the molecules have kinetic energy. Could be anything. Could be solid, liquid, or gas. Thermal energy is also based on molecules, but it's the total kinetic energy of all of them. So my favorite example, as you know, is an iceberg has a lot of thermal energy because there's so many molecules, even though on an individual basis, they're not moving very fast. All right, you read the question, you realize, okay, obviously heat is going to flow from the hot thing to the cool thing. So I think it's pretty obvious what's hot and cold in this situation, and it's going to flow from the marbles. Heat always flows. It says explain. So you got to say because heat transfers from a hot thing to a cold thing. Now when we get to parts B and C, you got to really understand this equation, Q equals MC triangle T, this one right here. It's really all about this equation right here. Q equals MC triangle T. Now, it says thermal energy gained by the water, so you're calculating heat for the water. Thing to realize is the change in temperature of the water. Look at the numbers. It's 5.5 degrees Celsius. And then we're going to plug that into the equation, which makes sense. Heat flow depends on mass. To change the temperature of a big mass or something with a lot of specific heat, you need a lot of heat flow. And if you have a big temperature change, you need a lot of heat flow. So they all make sense. Mass, specific heat, temperature change. Notice the specific heat is in joules per gram, but they gave us grams, so we're good to go. Plug it in, you get 1,728 joules. Okay, fine, there's my answer. Don't forget to put units, joules. Now, calculate the specific heat of the glass. This is a little bit harder, but you just realize that for the glass, the heat is the same. Heat out equals heat in. We did a lab on that. And then the temperature change of the glass was 74.5 degrees Celsius because it went from 100 to 25.5. And then you plug into the equation. When you put everything in, you see your heat flow Q, you see your mass of the glass. Yeah, mass of the glass. And I'm realizing, oh, okay, yeah, sorry. I underlined the wrong mass before. The mass of the water was 75, so I was just second guessing myself. And then when you plug this, when you get to the next step of the algebra, you get this, and then you solve for C, and don't forget to use the correct units. But they already gave you units right here, so you're good to go. Question 22, kind of tricky. This is really about momentum. They're talking about slowing an object down. Whenever they talk about collisions, you're talking about momentum, or you're talking about this thing, which is impulse. So if you look at this equation right out of the equation sheet, and remember that this is available on the exhibits, F triangle T equals triangle P, you can see that if you look at all these choices, and knowing that triangle P is a change in momentum, and momentum is mv, only a couple of these actually have to do with force, time, mass, etc. The height would make for a larger velocity, and the mass of the water balloon would require more force to stop as well. It doesn't matter how quickly we drop them or the temperatures or the time that we wait. In this question, it's obviously about forces. The net force is 0. They're all balanced, so that there's no acceleration, so the velocity would be constant. That's based on F equals ma and inertia. The inertia keeps it going. If you apply a greater force, then you're gonna make the arrow longer. Okay. On to the next one. in this one, we've got an elevator, and we're saying plug into PE equals MGH, and then you'll get an answer when you plug in. They wanted the whole thing, so I guess you're just going to do 400 kilograms times G. Remember, G is always 10, and that can be found in your exhibits. Remember this. It says down here G is 10, and then we also know that force weight is mg, and we also know that's the same G here for potential energy. So plug in and you'll get an answer. I think it works out to be 16,000. Here we've got some waves. This is interference. We've got two wave pulses coming at each other, a crest and a trough. Positive amplitude, negative amplitude. It's going to be interference, and the resulting amplitude is going to be 3 minus 1. Now for number 26, we're using V equals IR, which again is right there in the equation sheet, right there. And V is voltage, so when you plug in the numbers, you will get the answer. It's going to be one of these answers. I don't know, just do 1.5 divided by 60. Number 27, acceleration on Mars. This one's tricky, but they're giving you this, they're giving you this, and they're giving you this, and you're going to solve for G. And I think it ends up being 3.75 or something like that, something that'll round to that. But again, just plug the numbers in. Oh, 5.7 joules goes here. Coulomb's law and law of gravitation, again, they're both right here. They have very similar structure. And the difference is, though, you just have to remember that with positive charges and negative charges, you can have two positive charges, they repel. Two negative charges, they repel. Opposites, they attract. In the case of gravity, it's only ever going to be attractive. So there's your answer. One can be attractive or repulsive. In number 29, when you think about this collision, they're going to move toward each other. This one's moving toward the stationary one, and then this smaller stationary block is moving off. This one's not going to stop, and it's not going to rebound. So it's going to have a positive velocity of 1.5, which these all show in the graph. But then it's not going to reverse, and it's not going to be at the same speed. So it's got to be choice B, because this is the only one where it's still going forward, but just going slower. Technically, that's law of conservation of momentum, but you don't really need to know that. I'm sorry, guys. This is just logic. I mean, I told you there's some things that I'm just going to throw at you in this video, and that's diffraction. It's when light waves bend around an object. I mean, this can't be a reflection, you know. So just use some logic here. Photoelectrons are not released from the penny. That just, I don't know, that doesn't happen. That doesn't really make sense, and I think you know that doesn't make sense. In number 31, this is very similar to Coulomb's law. How can we increase the potential energy? Well, when you push these closer to each other, they're going to be harder to, when you push them closer to each other, it takes work to do that. If you were to pull them apart, they kind of naturally want to do that anyway. So the answer is B, decrease the distance, and there's going to be more energy. Now, stored in the field, that doesn't really matter. What matters is you just think, does that build up energy? It's kind of like pushing or pulling a spring. You can store energy in a spring by pushing on it or by pulling on it. And remember, in these videos, the whole point is to listen. Like, you know, you gotta take advantage of the wisdom. Take advantage of what the teacher's saying. Okay, so here we have force and time. And so for this first part here, you're just going to do force multiplied by time, and you can see that one of them is greater than the other because that force multiplied by time gives you the change in momentum. Now, for the next one, the change in velocity, this is a little tricky because if you look at x, it has a change in momentum of 30, but a mass of 10. So it changed its velocity by 3. And then if you look at 8 times 3, because again, we multiplied force and time. So now if we multiply force and time for this one, it's 24 divided by 6. It's going to be 24 and 6. So you can see there's actually going to be a greater change for y. Let me check my answer and see if my logic is correct. Yeah, there's less change than you have for object y, because even though object y didn't get as much impulse, 8 times the force times time was less, it's got a lower mass. Funky situation, this is called the Rube Goldberg machine, and then they want to relate it to a bunch of stuff. Here's Ohm's law again. If you think about it, if we want to make this light bulb brighter, just use Ohm's law. We either want to have more voltage or less resistance. And there's one choice that has more voltage and less resistance, so it's clearly brighter. That's choice C. Number 34, the marble fell. There's 2 ways to do this. You could think about the change of potential energy. But if you look at the force, if we look at work, we need force and distance, and the force is mass times g. So the force is literally 1. 1 times 0.25. So the answer is 0.25 joules. This one, just use some logic, and there's only one that makes sense. If we compress the spring more tightly, for example, that's just going to launch the marble even farther, which we don't want. Got to know your energy definitions, and then you know that before the spring was released, that had elastic potential energy stored up in it. And then, again, knowing the energy definitions for this one, the elastic potential energy gave the marble kinetic energy. Efficiency can never be over 100%. That's a big hint I have for you, because you can't get more energy than you started with. So the energy out divided by the energy in. The energy out was when the output of the spring was 1.8, and the energy that was put into it was 2. So you do 1.8 divided by 2, and you get 0.9. That's same as 90%. Here's my 3-part question. Both of them have 0 net force because they're not moving. They have the same mass. They must have the same mass. Their weights are creating an equal tension force. And the net force is no longer 0. It's now downward because we had extra mass, which creates extra weight. Here we have mass times velocity again. Do the math out and you end up with choice A. Just multiply mass and velocity. The kinetic energy was kind of irrelevant. Okay, you want to know about electromagnetic and mechanical waves, particularly comparing their speed, their medium, and their vibration. So I'll go through those real quick. As you know, electromagnetic waves are like light waves, and they go wicked fast at the speed of light. And that's also on your reference sheet here. Speed of light 3 times 10 to the 8th meters per second. Mechanical waves are like sound waves and other waves, and even when they go through solid, they still don't go nearly as fast. So speed of light, electromagnetic waves have a much faster speed. If you think about the medium, electromagnetic waves do not need one. They can go through a vacuum. Okay, they can go through a vacuum. Now, a vacuum doesn't mean a vacuum cleaner. It means empty space. They can also go through a medium, but mechanical waves absolutely need a medium, whereas electromagnetic waves don't. The vibration has to do with the perpendicular and parallel thing. Electromagnetic waves, the particles or the fields, they vibrate perpendicular to the wave velocity. But in mechanical waves can be transverse, or they can also be longitudinal. Meaning the vibration's parallel. Number 40, Q equals MC delta T. 3 additional measurements. There's 3 that have nothing to do with this equation. Volumes, for example, don't have anything to do with this equation, but we do need to know initial and final temperatures so we can figure out the temperature changes. Number 41, the best illustration of this would have these 2 balancing because it's on a surface, and then this force making it accelerate to the right. And the acceleration is based on the net force, which is 50 newtons, because these 2 cancel out, divided by the mass of 3.2. So you're going to do 50 divided by 3.2. Number 42, we're dropping a magnet. And remember that a magnet, current and magnetism go together. Electrical current, there you go.